symptometries, but the approach I will take is from Groupoids. So they're sort of analogous. And then once we have a C-star algebra associated to a graph or a dynamical system, we can ask how well this C-star algebra remembers this dynamics. So you can ask whether something like conjugacy, which is just saying that the dynamics is really the same, how is that reflected in the C-star algebra? And we'll see that a certain kind of orbit equivalence will play a particular role. So that's what I've emphasized here, the continuous orbit equivalence. We'll get back to that. And then finally, I'll end up with some perspectives. If I have time, I'll talk about both of them, but we'll see how we go. One is I find interesting is that inspired by graphs, you can get results that really extend outside of the realm of graphs. So it's an instance of having a structure you see at the level of graphs, but then it applies much more widely. I think that's an interesting perspective to have. And then there are some other kinds of dynamical systems coming from symbolic dynamics that are called suffix shifts. And the reason why I'm emphasizing them here is because they're actually modeled not by graphs, but by labeled graphs. So by taking this extra level of complexity, you get a larger class of dynamical systems. So I'll briefly touch upon that in the very end. So I've prepared to say this, talk about this, but please, if you have questions or comments, just interrupt, and then we can talk about it.
What are you labeling your graphs with?
So in the case of suffix shifts, you have a finite labeling set. And so when you just have a finite directed graph, you imagine that each graph has its own label. But for suffix shifts, you allow for some of the labels to be the same. So it's sort of it's a quotienting, a kind of quotienting. Okay, so just to get the very basics done, a directed graph, and just also to establish some notation, is just a set of dots and arrows, and I specify the orientation. So that's given by the range in the source map. And I've drawn for you quite a few examples here. They're interesting in their own rights. So maybe you recognize some of them. This is what corresponds to the O2 C-star algebra we've already heard in last talk. It also corresponds to the full shift. I'll talk about this later. I also wanted to mention that if you've worked with graphs in their C-star algebras, there's this annoying thing of having to choose a convention. And I think the convention I'll be talking about now is the same as in the last talk. So this thing is a sink, so a thing that possibly something goes into the vertex here, but nothing goes out of it. That's a sink. And one of these things is an infinite emitter. So these double arrows tell you that there are infinitely many edges going from this thing over here. And so usually, so it's easier if I draw them with a hole inside to say that these are the so-called singular vertices, and they're the ones that will give us some trouble when we start doing dynamics actually.
Maybe,
so I just wanted to.
Could you please draw the graph of a Teplitz algebra, and I'll be sure what convention you are using.
Sure. So I'll do it like this. So the Teplitz has a single. Yeah.
That's the old convention. Thank you.
Yes, it's the old convention. I have to say this is the one I grew up with, but I'm also trying to learn the opposite convention. It has its advantages as well, but you have to somehow come clean when you talk about these things.
It's like driving on the left or driving on the right.
Exactly. Yeah, and you need to stick to one choice.
Exactly. Doing both is not advisable. Yes.
No. Good. So this is just getting notation straight. So the first level is dynamics. So I'm actually more interested in the dynamics you get from a graph, and really it's actually quite simple. So the infinite path space with E infinity here is just you imagine you run along the edges of the graph, and it's just all the infinite collections of edges where the range matches up with the source. So that's fairly simple. And for this thing, there's no obstruction. So whenever I have an E, I can do an E again, or I can do an F. So this is the classical Cantor set, two symbols, infinite sequences into symbols. And for something like this, you get, I've written it out like this, but really what you get is the compactification of the natural numbers. So all of these, you have a single accumulation point and all the rest of them will be discrete. So this is really just the natural numbers compactified. And
By the way, do you know what this graph F represents? Do you remember?
So this is some quantum SU2, right?
Exactly.
Yeah. So unfortunately, I don't know too much about this, but I think it's fascinating that such a simple graph gives you such a small graph gives you these interesting examples.
Mm-hmm.
Right, so that's the infinite path space, and the shift operation, that's the dynamics that comes from this, is really very simple. It just forgets the first letter. So if I take such an infinite sequence, it just spits out the same thing where I forget the first edge. So this is like a time evolution. That's how you should think of it, that you draw out the trajectory, and the shift operation tells you that a day has passed and that you forgot the last step. So because we have these singular vertices I've mentioned down here, the ones that are either something like this, if you want to do C-star algebras or dynamics with graphs that contain these things, then you need to be slightly more careful. So you need to take all the infinite paths, but also all the finite paths that end in these singular vertices. So an example of this is something like this. Here, there's no infinite paths because there's no way I can go infinitely long, but the boundary paths actually has two elements, because I view a vertex itself as a path ending in the vertex, and I view this edge as something ending in that vertex, which is singular. So that's why I get two elements here. It's just to say, for nice graphs, it's enough to look at the infinite paths, but if you want to generalize, you have to be careful with the singular vertices. So that's the first level. That's the dynamics. So, and moving on to the next level, sorry, I wanted to mention before moving on to the next level that this really uses the orbit of a point. So usually in dynamical systems, an orbit is the point, and all the steps all the places you land when you iterate the map. That's usually what happens when the map is invertible, but in my case, I forget the first letter. So that means the map is not invertible. So I get this complicated expression of what the orbit is. And it's actually not so complicated. It's just saying that to be in the orbit means that I can shift it forward, but it should also be all the things that have maybe some tail that land in that shifting forward. So maybe it's easier to see if I write it like this. So a point y is in the orbit of x, precisely if there is some iteration of x and some iteration of y, so that they agree in the end. I find it instructive to look at a drawing like this. So if the line here is the x, then maybe a y is something that comes in here. So it means that they don't agree all the time, but I can shift it some amount so that they agree. That's what it means to be in the orbit for an irreversible map, and that's what we need to consider here. And this plays a crucial role when I go to the next level of the groupoid. So I'm not sure how many of you are familiar with groupoids. I don't want to give you the general definition or construction, but really be specific about the graph groupoids, because it's something you can write down. So the groupoid is really an algebraic object. And the way it's constructed here is that from a graph, you get a triple. And the two of the entries are points in the infinite path space or boundary path space. So sequences along the graph. And they should be in the same orbit. So I have this condition here. This is exactly what it means for them to be in the same orbit. And what I also record is not the K and the L, but the difference between them. So the central term here is an integral value. So things of this form are elements in the groupoid. And like in a group, I can multiply them, but only when the source of this thing matches up with the range of this thing. And if it does, then I forget this y and I add up the integer values. So I get something like this. It's just a multiplication operation, partially defined. And just like in a group, I can invert everything, and the inversion is just flipping the 2 points and then putting a sign on the integer value here. It's really convenient for a few reasons. So there's a convenient way of defining a C-star algebra. I'll talk about this in a minute. But the other thing is, I really want to emphasize that this takes the orbit into account. And the orbit is in general not either closed or open. It's topologically not interesting. So that means that the classical orbit space you'd get is very badly behaved topologically. So in some sense, this groupoid should really be viewed as a proxy of this orbit space. It's somehow the replacement for the orbit space. And the good thing about this replacement is that it's actually topologically very well behaved. So I think this is in line with the philosophy of non-commutative geometry, that sometimes spaces are not enough. And then you look at these non-commutative spaces with extra structure. So really you should think of this as the non-commutative orbit space of the action, of the shift on the path space. And one more thing to note here is that if you look at the ones where the x and y agree, so there's just x and x, and the middle term is 0, then this is exactly a copy of the boundary path space. So in some sense, the groupoid consists of arrows. Formally, it's a category. So it consists of arrows or elements like this, and its range and its source are really elements of the boundary path space. So they're really, the unit space is the original space itself. And then these orbits, these arrows incorporate when points are in the same orbit. So it's a very, very brief description of the graph groupoid, but the good thing is it's very concrete, and the good thing is that it's topologically very well behaved. And that leads us into the third part now, that the graph C-star algebra. As I said, sometimes this is, maybe usually it's described from generators and relations, but I want to emphasize the groupoid picture for several reasons. And one is actually that the first general definition of the graph C-star algebra came from a groupoid, exactly this groupoid. And I don't want to go into the details of how you go from a groupoid to a C-star algebra. I just want to give you the very basic gist of it. What you do is you look at the groupoid and look at all the complex valued, compactly supported functions on it. And when you do that, this has some extra nice structure. So actually you can define a product. This is a convolution product. It's given like this. This is your usual convolution. And it's actually a star algebra with this product, and the star being inverting the element, the groupoid element. So remember that I can always invert a groupoid element just by flipping them, and then a complex conjugate on top. So this gives me the structure of a complex star algebra of these functions. And then the C-star algebra is then a suitable completion of this.
Just a quick question.
Yeah.
You mentioned this compactly supported function. You mean just finite support, yes? Everything is discrete, yes?
Not right. Okay, so good. Not everything is discrete. Let me go back one slide. I do have a topology on this thing. And I didn't mention that. There is a topology coming from the original space here. Gives me a locally compact Hausdorff topology. And this groupoid is a tal. So that means that the fibers are discrete. And that's really the reason why this is always finite, why this is well defined. But the groupoid itself has a topology.
So the unit space has non-trivial topology, right?
Sorry, say it again.
The unit space of a
Yes.
groupoid.
Yes,
Usually
is a Cantor set in many cases.
But
Can you
still in
say
this
a bit more
formula,
how it's generated with topology?
Yeah, sure. So I can write down, I can write down. Okay, not so pretty. These things are cylinder sets.
Mhm.
U and V are open sets in the original space. They're open in here. And elements in this cylinder set look like
So,
X.
and with original space, with tweedledee E, with what, infinite paths in your graph?
Yes, so
Okay.
boundary paths or infinite paths. Just think infinite paths.
Yeah, yeah.
So I take open sets in the original space,
Mhm.
and then I look at the elements where X is in U, Y is in V,
Mhm.
and then the middle term is just K minus L. These sets form a basis of
Okay.
compact open sets, actually. So it's a zero-dimensional space. And they generate a topology. And maybe it's worth saying that this topology is strictly finer than the product topology you would get just looking at the topology you get from the product of the space, the integers in the space.
So there are more open sets like this.
Yes, yes.
Mhm.
The important point is that it's all very concrete. You can write down everything from your starting data. There's no mysteries here. Obviously, I'm not telling you all the details, but it's very concrete.
But I have a very naive question about this particular slide. So if I remember correctly, there are some conditions on a graph. So let me take the usual definition of a graph sister algebra, whatever the usual means.
Yeah.
You are with me here. And is it not true that you need some conditions on your graph to make sure that your graph sister algebra is indeed the groupoid sister algebra for a particular groupoid? Is it your claim that this is a graph sister algebra presented by a groupoid? Does it work for absolutely all crazy graphs?
Yes, that's my claim.
Okay.
Yeah.
Cool.
And this was the first, at least for row finite, this was how it was first defined.
Because I have some recollections about graphs for lens spaces where there was a
Yeah.
by Szymański and collaborators. Yes. Is a graph sister algebra, but we have to exclude some cases of lens space if something is not coprime. And so this is why I had this flag raised in my mind.
Right. That might, I'm not sure exactly if that was to ensure that it is a graph algebra.
Mhm.
But once it is, then you do have a groupoid description. And for those, I think for those examples, actually, the path space is not a Cantor set, it's a countable set, actually.
Okay. Okay.
So
Cool.
it's quite, yeah.
Thank you.
I'm sorry, still, even that the topology is no longer discrete, still in this formula for defining the convolution, you are using ordinary sum. There are no integrals, yes?
Exactly. And that's because the groupoid is a tal. And that allows me to exchange integrals and just write sums.
Okay.
So that's an important point. That's an important point. Thanks for asking. In more generality, you have to use integrals, and then you have to specify a collection of measures for this to make sense. But for graphs, we're lucky that we don't need to do that. Counting measure works.
Okay, thank you.
So the upshot here is that you can build a groupoid, and you can build a graph from a groupoid. And then the one more thing I want to mention is that when you do this construction, you get the C star of the groupoid, but in fact, you get a very important subalgebra. This is the diagonal. So these are just the functions on the unit space, functions on the original space, and they sit inside of this thing very nicely. So sometimes I'll write D of E because it's usually called the diagonal subalgebra. And I'll show you why it's important in a minute. A priori, you should think that it's important because this C-star algebra, I mean, C-star algebras can be beasts, right? They could be big and complicated. But this particular abelian subalgebra is very intimately connected to the original information I had. So if I'm interested in how well a C-star algebra remembers the original information, I want to keep track of as much as I can. And this is one instance where I can see the original thing appearing in the potentially complicated C-star algebra. Good. So 3 steps: the dynamics, the groupoids, and the C-star algebras. And then I want to talk about, this is a way of associating a C-star algebra to a graph or a dynamical system. But what happens if I take 2 things that are the same, two graphs that are give you the same dynamics? They might not be the same as graphs, but the dynamics could be the same. And that's what's called a conjugacy. And a conjugacy is really just a homeomorphism of the path spaces that intertwines these actions. That's how you should think of it. Something that both preserves the topology, but also the action. The reason why I have to be slightly more careful here is because we can have annoying trouble vertices in graphs. So if you look at this first example down here, the graph algebra of the dot, just a single vertex, is the complex numbers. And the graph algebra of this loop is the circle. And we would not want these 2 graphs to be conjugate because we want conjugacy to imply isomorphic C-star algebras. And the circle is obviously not isomorphic to the complex numbers. So, and you'll see that if you start writing down the definition, then actually in one direction, this will satisfy this condition, but in the other direction, it will not satisfy this condition. So you need to be careful and say that you have to have a homeomorphism that intertwines the shifts, but it has to do that also with its inverse. And that will exclude something like this, a bit pathological case. But when you think of it, you should just think of it as a homeomorphism intertwining the shifts. And then another example of something that is not conjugate is if I take this usual picture of the Kunz algebra, and I take this thing, which is very similar, but you want to think of taking this one loop and just extending it, so making it slightly slower. So one loop is now sort of expanded like this. And the reason why these 2 things are not conjugate is more subtle. It's just you can view that at the level of entropy of the, you can see it at the level of entropy of the dynamical systems. So conjugacy is actually quite a rigid thing. So even if things look quite the same, they asking that the conjugate is quite rigid. That's what I want to say. And you can describe very accurately precisely when these graphs are conjugate, and that can be done in terms of certain splitting operations. And I think Søren Eilers will talk about this in his talk later about how you perform certain graph manipulations, graph moves, and that will induce, for example, conjugacy or other things.
Can
So,
I
but
ask a question?
Yes.
Does the conjugacy necessarily preserves the length of the paths for the finite path that ends in a singular vertex? Is it
does.
necessary? It does? Okay.
Yes, it does.
Thank you.
Yeah. So conjugacy is quite restrictive in that. So if that's the case, then we'd also expect it to preserve a lot of the structure. So in this slide, I want to go through the 3 steps again of the dynamics, the groupoids, and the C-star algebras, and then show you how you see that things are preserved. So at the top, I assume I have a conjugacy, let's call it H. And in a very concrete way, it induces a groupoid isomorphism. So remember, elements in here look like these triples where I have 2 points and an integer. And you can just very naively apply the H to the component of the infinite paths and leave this middle term as it is. And you will get, if you sit down and work it out, you'll see that this is actually a groupoid isomorphism. And moreover, if I restrict to this unit space, sorry, this should be GE. So if I restrict to this unit space, then I get the original map back. So remember, inside of the groupoid, it has the original space sitting inside. So if I restrict this map, psi, then I recover this original map. So it's a very naive thing to do. You just apply the H and you see that it's well defined. You see that it's an isomorphism. And then at the level of C-star algebras, remember that the C-star of the graph is the completion of the functions on the groupoid. And the first thing you try here, if you want to get a star isomorphism, well, it's to use your original map psi. And in fact, that's exactly what you can do. But you just, the isomorphism at the level of C-star algebras is just induced by the psi, like this. And that gives you an isomorphism.
Can I ask, Kevin?
Yeah.
Isn't the middle thing in the groupoid isomorphism, does it have to send P to P? Or isn't it P to some?
So for a conjugacy, it does send P to P. But that's an important point.
Okay, now I understand what you're saying. Okay,
yeah,
sorry.
Yeah. So I have to be more careful when I look at orbit equivalences. But in this case, it's all right. Good. So just wanted to mention, such a nice map on the groupoids gives you a nice map on the C-star algebras. Again, remember the C-star algebras contains a copy of the functions on the unit space. And if you look at things coming from the unit space, it's exactly the induced map from the original homeomorphism. So everything is aligned very nicely. Okay, so that's just going through the steps again, but now with a map, the conjugacy. And then here's a theorem. And there's a lot of names to attribute. And I want to, let's forget about the first part just for a second, and then the second and the third part. So what I just told you is that if you have a conjugacy, that gives you an isomorphism of groupoids. So that's something like this. And it also gives you an isomorphism of C-star algebras. And the way this isomorphism is constructed, you can see that it actually takes the diagonal onto the diagonal. And we call these diagonal star isomorphisms. So you might want to think, well, how well does this information remember the original dynamics? And I mean, in the best of all worlds, you would hope that it's exactly the same as conjugacy. But this very nice theorem tells you that this is actually not the case. And it's not so bad at all. It's actually quite nice. Instead of conjugacy, it's sort of too restrictive. It's asking too much. You can recover the original dynamics, but only up to a kind of orbit equivalence. So orbit equivalence is what you expect. It's a homeomorphism that takes an orbit to an orbit. And this continuous, I'll try to explain what this means. Roughly speaking, it says that an orbit equivalence will take an orbit to an orbit, and the continuity will tell you that you can only stretch that orbit in a continuous way. So you have continuous maps that tell you how you can stretch that orbit. You can't do it in an arbitrary way. And this very nice theorem tells you that when you have graphs E and F, then say the C-star algebras are diagonally isomorphic precisely when the graphs are orbit equivalent in this continuous way. And I should say that Matsumoto was the one who came up with this notion of continuous orbit equivalence. He did not use groupoids. He went straight to C-star algebras. Matsumoto Matsui had a very nice paper where they explained this thing and also explained the stabilized version relating to flow equivalence. So I wanted to mention that Søren's question to Bishan at the end of the last talk, he mentioned flow equivalence, and flow equivalence corresponds to exactly this thing, but when you stabilize by the compacts. So you should really think of continuous orbit equivalence as the analog of flow equivalence. And this is you can make that more precise, and there's a whole analogous story you could tell about stabilizing here and then looking at flow equivalence instead. Of course, I had to choose some things to talk about and then leave out some other things, and so I chose to emphasize this orbit equivalence instead. So this next paper, Carlson, Eilers, Restov, Ortega and Restov, they extend the result of Matsumoto Matsui from the simple case to the non-simple case. And then Brownlow, Carlson, Whitaker extend to directed graphs. And that's why I put in this nice thing, because there are some conditions you need to impose for this to be formulated nicely. And then maybe anticipating what I want to say in the end, this paper by Carlson, Ruiz, Sims, and Tomford really takes this exactly the same idea, exactly the same theorem, but extends it from graphs to very general dynamical systems coming from local homeomorphisms. So I'll touch upon that at the end again. So there's a lot to say here, and many people involved, and it's sort of taking one step at a time, starting with finite, strongly connected graphs. That was Matsumoto. Matsumoto Matsui made this observation to groupoids, and this was then extended to the non-simple case by Carlson, Eilers, Ortega, Restov, and then to more general graphs by Brownlow, Carlson, Whitaker.
I have a question. The nice
yeah.
part there is conditional or something else?
Yes, yes.
Conditional
exactly.
is sufficient. Okay.
Yes, and the issue is that you can, the thing is, I think you can remove that, but then you need to ask for this orbit equivalence to be slightly nicer. And I just didn't want to add all kinds of adjectives to this. Yeah. Good. So maybe I should be slightly more precise about what continuous orbit equivalence means. So now we have conjugacy, that it's sort of self-explanatory, that it would be interesting because it's exactly when the dynamics are the same. But dynamics is also very interested in orbit equivalence because sometimes conjugacy is just too difficult. So let me be precise about a homeomorphism being a continuous orbit equivalence. That means this complicated expression. So it's not so important exactly what is said here, but let me try to just say again what you really should think about. You want to take a point X, and then you want to take its shift, and you want to control how far away H sends X and its shift. And I mean, they can be mapped to very different places, but the point is that they should be mapped only so far away that there is a continuous L and a continuous K that allow you to shift them to each other. So the orbit is exactly some things where X is related to its shift, and H should send that to something in a way that you can control it by continuous cocycles. That's the point of this thing. So this continuity of the maps K and L is really essential. And again, you need the analogous thing for the inverse map here. But that's all it does. Controls the orbits, but it tells you that you can only stretch them in a continuous way. And this was pioneered by Matsumoto, who just somehow immediately saw that this was the same as diagonal star isomorphism. There was no mention of groupoids or anything. Sorry, so let me go back to the slide before. I just want to emphasize once more that this really formalizes this idea that the groupoid is the non-commutative orbit space, because the isomorphism class of the groupoid precisely captures the orbit equivalence class of the dynamical system. So I think that's really nice. It's really a formal way of saying that it's the right proxy for the orbit space of these dynamical systems coming from graphs. This is the definition again. And then I wanted to give you just a few examples. So we saw this example before. I told you that these two things are not conjugate. The reason being that this is the full shift. So this has entropy log 2. This is not the full shift. It has, it's usually known as the golden mean shift, and because its entropy is the golden mean, and the entropy is an invariant of conjugacy, so they cannot be conjugate, but they are continuously orbit equivalent. And you can actually, I mean, you do really map this edge to these two edges, but you see that it's continuous stretch. It's just one thing mapped to a step 2 thing. That's a continuous stretch, and you can write down the explicit orbit equivalence, and you can check that it satisfies all these things and gives you diagonal star isomorphic C-star algebras. And you might know that this gives you O2. So now you know that this also gives you O2 as its C-star algebra. And then a different example is this thing O2, but now with this hideous thing attached to it. This is usually known as the Kunz splice. And these two things are not continuously orbit equivalent, and they're not flow equivalent. I mentioned flow equivalence before, and this is simply because there are some very basic invariants you can compute, and they are not the same. Good. So conjugacy gives you isomorphism of groupoids, diagonal isomorphism of C-star algebras, but conjugacy is not, that information is not enough to retrieve conjugacy. So that's why I'm asking this question now. Is it actually possible to completely characterize conjugacy in terms of C-star algebras? And so that's what I'd like to talk about now. And again, there's a few steps to make. And so the key point is that diagonal isomorphism of C-star algebras is not enough. That will only recover up to orbit equivalence. So the question is, what extra information do we need to keep track of in order to recover the original thing up to conjugacy? The first step to doing this, I'll just very briefly mention this. I did this in my thesis with Toke Carlsen, and what we did is to define a very concrete, completely positive map on the C-star algebra. And it turns out that if you keep track of these two things, as I mentioned before, these two things with this completely positive map, then you can recover the original thing up to conjugacy. So that answers the question, but under some very restrictive conditions, namely the graph should be finite and it should be essential. Essential means any vertex has both incoming and outgoing edges, so there's no trouble vertices. And the issue is that these conditions are really quite restrictive, and it's not obvious how to extend this. So basically, we needed a new idea to go to, say, graphs, more general graphs. And this is something Matsumoto did, and I'll try to explain what that extra information differently, how you'd need. So Matsumoto, I guess, saw this result and was not happy because he wanted something involving the gauge actions. And the gauge action is something I've not mentioned before, but I imagine everyone working with graph algebras knows that there is a gauge action on the graph algebra. It's fundamental to studying its structure. And I haven't told you anything about it, but now here we go. So let me explain it in this way. Say, if I want to recover a conjugacy from some C-star algebraic data, then I have to keep track of more information. So let me go through the same slide as I did before, but now showing you that there's more information preserved than I mentioned the first time. And one thing is actually, Søren anticipated this by asking about this integer component here. So a conjugacy, again, induces a groupoid isomorphism in this very naive way. And I just said, well, it's a groupoid isomorphism. But in fact, you notice that this integer value is preserved. So you could say that if you define a map to take a groupoid element and spit out the integer component, this is called the canonical cocycle. Then this isomorphism intertwines these canonical cocycles. This is some extra information that's preserved. And the nice thing about this is that the canonical cocycle, this maps into the integers. This induces an action of the C-star algebra from the dual group. So from the integers, the dual group is the circle, and you get an action of the circle on the C-star algebra. And this canonical cocycle, you can check, it gives you the canonical gauge action. So this means when I have a particularly nice isomorphism preserving this cocycles, it means that the induced star isomorphism preserves the canonical gauge actions. So this is one more step of information that's preserved, which is really nice. Unfortunately, it's not enough. I'll get back to this. So let me very briefly tell you that you can even go a bit further than this. I told you that the canonical co-cycle is the thing that just spits out the integer value, and this induces the canonical gauge action. But in fact, you can look at other co-cycles. You can look at other maps into the integers. One expression is given like this. I just wrote it down. It's not important what it is. But what is important is that it comes from a function on the original space. So here you might just want to think of putting a weight on your edges. So if I just put a weight, different weight on my edges, then I can define a function like this. And the co-cycle here takes this weight into account. And that gives me a weighted co-cycle on the groupoid. And in turn, that gives me a weighted gauge action on the C-star algebra. So the weight comes from putting different weights on the edges, and that gives me a whole family now of gauge actions on the C-star algebra. And the important thing is that the conjugacy, as I said before, it respects the canonical gauge action, but in fact, it respects all these weighted gauge actions as well. That's the crucial observation. Any questions to this? I'm being a bit brief about how this is defined. I just want to tell you that it can be done.
So how come but now it's not a circle action, but real line action?
Right, that's, I guess, oh, maybe I was being, I mean, you can actually, you can do weights that just map into the real line, and then you'd get real. Maybe this was a typo that actually there's many different functions you can choose here, and that will give you actions of the real line instead. So maybe this was a typo.
I can tell you why I'm asking this question, because
Yeah.
in many examples, the gauge action is actually free. And this is a very nice property because you have something like a principal bundle. But I cannot imagine that when you would have R action here, it would be free.
Right, right. So but if F is particularly nice and just has some integer values on the edges, I'm not sure if that gauge action could be free, maybe. Not sure.
Anyway, thank you.
Yeah, so, and just to say that if I choose F to be the constant one function, then I do recover this thing up here, because you'll see that if F is just constantly one, it just counts the terms of this sum, that's K, and it counts the terms of this sum, and that's L, and that means I recover K minus L here. So the weight, if I just put the weight one on each edge, then I do recover the canonical gauge action. This is an example to show you that unfortunately I have to take this extra step of generality of these weighted gauge actions, because these two graphs are examples where we can show that they are actually isomorphic in a diagonal preserving way, but also in a way that intertwines the canonical gauge actions. But you can also check that they are not conjugate. So this is a bit annoying, I guess, that this triple of information is not enough. It's very close, but it's not enough. So you need to take one more step of generality and take these weighted things into account. So just to say that it is unfortunately necessary to take that extra step. And really, so these graphs look very much the same. And what you should think of is just taking one edge here and then moving it to the other side here. It's sort of a move. And maybe Søren will, I'm not sure, but maybe Søren will talk about this move as well. It's a different kind of move to what I mentioned before.
I will.
Okay, good. So this is called a balanced in-split, and it's sort of designed to give you examples like this, where it's very, at the C-star algebraic level, very nicely behaved, but the graphs are usually not conjugate. Good.
Sorry,
So the
I have a-
punchline.
I have a question.
Yes.
In this example, what are these weights distinguishing these two?
You can put weights on, let's see. That's a good question because I did work it out, but it's a long time ago now. I think you could just put weight on this edge that you move, something not one, and then it's not preserved.
So these gamma
is
E,
in-
gamma F are weighted gauge actions.
Sorry, so these gamma ones, they're the canonical gauge actions.
Uh-huh.
So the canonical ones are preserved.
When I don't understand the question about weight.
So I think the question is that
Because canonical gauge action doesn't distinguishes them.
exactly.
Okay.
Yes.
Okay. Yeah. Mhm.
So they are very closely related, but they're not conjugate. So that means that it's not enough to just look at the canonical gauge action in order to distinguish them. And so this is the punchline here, that two graphs, no conditions, are conjugate precisely if I have an isomorphism that preserves or respects in a suitable way all the gauge actions weighted by functions coming from integer valued things on the path spaces. So I had to take a few steps to make sense of what this means and also tell you that I can't get away with something easier. I can't get away with just looking at the canonical gauge actions. I have to look at this whole family of gauge actions coming from functions in here and here. And so I should say this is Matsumoto did this kind of theorem first in the case of simple Kunstkrieger algebras. For some reason, he focuses almost solely on simple C-star Kunstkrieger algebras, even if you can extend those results. So what we did is to first, we wanted to do a result for graphs, which took some work, but then we realized, as I mentioned before, that actually this is not dependent on the graph. So our real main result is the next thing here, that exactly the same kind of conclusion, having a star isomorphism, preserving this gauge actions weighted by these functions, precisely captures the conjugacy class of not just graphs, but very general dynamical systems coming from local homeomorphisms. I think I forgot to say actually that when you have a graph, the shift action is always a local homeomorphism. So when it's natural, when you understand graphs well, it's natural to ask whether these phenomena you see actually applies to the dynamical systems just coming from local homeomorphisms.
Sorry, could you go back to the previous slide
Yes.
for a second? So this looks like a very beautiful theorem, but could you, for instance, given a function, so it's vanishing at infinity and integer valued, so I guess it must be compactly supported.
Yeah.
And now I'm giving you such a function. Can you write for me the gauge action in particular? How does a group depend on this function? Because we saw it could be T, it could be R. What is the formula? You have such a weight function, and I want to see explicitly a formula for a gauge action. Can you do it in some succinct way?
I can. Let's see if I can do it. So what I would do is take F in C0. And then let's say that I label it like this. And it's easier for me to do at the level of things in the groupoid. So remember the C algebra is the completion of things of the groupoid. So if I take such a function, I want to tell you what this is. So this again should be a function on the groupoid. So I have to evaluate it at an element in the groupoid. And what this should be is I evaluate the original function at the element of the groupoid. But now I take this co-cycle I got from before, that I can go back to so you multiply by this value of the co-cycle at that groupoid element. So let me just briefly go back. So this function defines this co-cycle that spits out some integer. Sorry, so I think
it is always so that if you have a co-cycle, it defines a dual action.
Yes, it's always the case.
So it should always be the circle, right?
Yes, sorry.
Okay,
I
so
think I
that's
put a
a-
typo
Let's
in there.
say
Okay.
a billion.
Yeah, okay,
Okay,
that's
so
this is what I was after. Okay, I'm very happy
Yeah.
now. Yeah.
So again, I mean, everything is, you can write it down concretely, what happens. Good. So this is really the main theorem of our work. This is with Becky Armstrong and Toke Carlson and Søren Eilers. And I think this is really nice because I like the theorem, but I think it's really nice because it's directly inspired by graph algebras, but the statement has nothing to do with graph algebras. So this is an instance of really being inspired by these things and saying something about very general dynamical systems. I think that's very interesting. And I should also say the previous theorem I mentioned about the orbit equivalence is also extendable to very general local homeomorphisms. And this was the work by Carlson, Ruiz, Simmons, and Tomford I briefly mentioned before.
I have a question.
Okay, so yes.
This context is a context of partial action. So,
Not quite, not quite.
quite.
So let's see if I understand what you mean. So partial action would be an action of a group.
Not a group. It's a inverse semigroup action.
Right. What I mean here is just a single map. I mean, I guess you could reformulate it like that, but what I mean here is just a single map, which is a local homeomorphism, so open and locally injected.
Yeah. So it's exactly context of inverse semigroups. So so on the one hand, it's more general. On the other hand, it's less general than more general groupoids, because it's an action by some
Yes,
group.
but so it's possible you could do a similar thing for more general actions of inverse semigroups. I'm not sure how that would go, but that's certainly possible. You could do that. The groupoids you get here are very specific. It's these Giacono-Renault groupoids, and the groupoids from inverse semigroups don't have to look like that. Okay, so sorry. That was the first perspective. I'm coming up on the very end of my time here. So the first perspective was just to say you can get inspired by graph algebras and get a result that really says nothing about graph algebras or says something much more general. I think that's very nice. And the second perspective, let me just spend 1 or 2 minutes. It's easier to explain with an example. So if I have a graph like this, but I label it by labeling from a finite set, so in this case, just 0 and 1, I can get some new kinds of dynamical systems that I cannot get from graphs, just regular directed graphs. And this one is usually called the even shift. And the reason is if you look at between any two ones, you can only have an even number of zeros. So this is a very interesting example from symbolic dynamics. It has its counterpart, the odd shift, which is, as you would guess, between any two ones, you have an odd number of zeros. And in fact, so there's a whole class of examples coming from labeled graphs. And there's a whole, you can run this whole machinery again, ask when are they the same, when are they orbit equivalent, And the reason why I'm mentioning it here is because the C-star algebras you get are actually graph C-star algebras coming from the underlying graphs. But the diagonal you get is different. So when you look closer, not just at the C-star algebra with its diagonal, you get something different. But then you can run the same machinery and you can show that these two, for example, these examples are continuously orbit equivalent.
Sorry,
And-
Kevin, let me ask you.
Yeah.
So for you, labels are like colors, right? You don't care that it's 0, 1, it could be an apple and an orange, right?
Sure. Just a
Because-
finite set.
Okay, because when I was using labeled graphs in combinatorics, we really needed a structure of some commutative semi-ring.
Okay.
Okay. Where the usual graph would be for the semi-ring of natural numbers. And the label n means that you have n edges going from vertex v to vertex tau.
Yeah, I think that matches up. So I just want to end with saying that there's a completely analogous characterization of conjugacy. But in fact, for this continuous orbit equivalence, it's more delicate. So with Toker, we showed that this orbit equivalence implies a diagonal star isomorphism, but the converse is still open. I mean, I believe that it certainly should be true that you have a characterization, but the converse direction is open at the moment. And so this is just a summary. Just want to say graphs give you very interesting dynamical systems. Continuous orbit equivalence should correspond to an isomorphism preserving the diagonal. Conjugacy should correspond to isomorphism preserving this whole family of gauge actions. And in nice cases, you can even extend these results outside of graphs to very general dynamical systems. So that's what I wanted to say, and happy to take more questions.
Thank you very much. So let's see, do we have more questions? Yes. Yeah.
I just want to first make a comment about the action of the circle and then the real lines. I think if you go to the real line, it's interesting to look at the KMS state for the action. I have considered that.
I thought about it, but I've not looked at it yet. It's certainly something I'd like to study, yes.
And another question that you talked about that tau map. Can't you replace this family of gauge action for the tau map and say that the isomorphism intertwines the tau maps? Isn't that enough also for conjugacy?
Right. So it does work in nice cases for finite graphs that look nice. The issue is that the way it's defined simply doesn't make sense for infinite graphs.
Yeah. Actually, I think we've done this recently for subshifts. Actually, in general for conjugacy, we did in the pure algebraic setting. We are now writing the paper for the C-star algebra setting, but we can also. It's a little bit more annoying because we have that sum that if you go to infinite graph, it should be infinite sum, but then you can replace this for some kind of finite sums. It's a little bit technical, but it can be done.
Oh, okay. It sounds very interesting. I'd be happy to see that.
Yeah. So yeah, if I can talk to you about this later, I guess.
Certainly. Yes. Thanks.
Okay. Yes. Here's another one.
So also about these generalized cocycles. So the canonical gauge action, the fixed point algebra gives you the AF core for the graph algebra.
Yeah.
So if you make one of these more general cocycles, do you have a sense of what the fixed point algebra would be? And in particular, if you use a cocycle to the reals, now you have an dual action of the reals. And I guess there are different ways of making a generalized fixed point algebra, which I have to admit I know nothing about. But I wonder if you know anything about what kind of subalgebras you might, or kinds of things you might get from that.
I know that you can get different structure on the fixed point algebras. You can make sense of. You can always make sense of the fixed point algebra, and you do get. They look different and behave differently. There is a paper by Matsumoto where he studies these fixed point algebras. I'm not sure at the moment where it would lead to study them, but there's certainly something you can say, yes.
And I guess what I was wondering is if there's some real cocycle that has some, well, I'm thinking of like the continued fraction AF algebras, which you can think of as graph algebras. And I haven't thought about this at all, but is there maybe a cocycle that is mapping into the, the K0 group as a dense subgroup of the reals that might give you something unusual, or I don't know.
Okay, so you want to factor through the K0 into the reals.
Yeah, well, no,
Okay.
so, choose a cocycle that's related to this extra structure that this particular graph algebra has, and hope that the fixed point algebra is something, I don't know, I have no idea, I'm making this up, but I just want to.
No, but there's certainly, what I'm thinking is that you can tailor these weights, these functions, to extract certain behavior. So there's certainly, I believe there's something you can do there to emphasize certain kind of behavior.
Thank you.
Thanks.
I have another question about the soft shifts, because in general, they are not local homomorphisms. So what do you mean by the diagonal in this case?
Yes, very good, very good. So actually, it's a local homeomorphism precisely when it's finite type. So the reason that what we can do is that so this is for suffix shift, there's always a canonical honest graph associated to it, and that's the underlying graph of the thing. So just forget the labels. So the diagonal, you have to be careful. Do you mean either the functions on the graph, I mean the path space of the graph, or there's a smaller thing that is the functions on the paths, but now with the labels instead of the edges? And I mean the second thing, the smaller thing coming from the paths of the labels.
Don't you also need that the diagonal only for the graphs also to be preserved?
Sorry, say that again.
No, you said that it preserves the smaller subalgebra, but don't you also need that it preserves the biggest subalgebra as well?
Yes, but that's actually automatic. That's that takes some work to show, but that's automatic.
Okay, see, thank you.
Yeah.
All right, thanks. Do we have any other questions? If not,
I have a question.
oh, there is one more.
So coming back to these cocycles, so the presence of this cocycle is related to the fact that you are considering these groupoids up to isomorphism. What about comparing them by equivalences of categories?
Yes.
Would it lead to replacement of this cocycle by some cohomology class of this cocycle? Am I thinking in the right direction? Does it make sense?
It does make sense. So one thing I should say is that, let me go back to the theorem about orbit equivalence. If I mentioned that orbit equivalence is related to flow equivalence, and so if you replace this by flow equivalence, then you replace this by Morita equivalence of the groupoids.
Yes.
And this thing by a diagonal Morita equivalence of C-star algebras. So there's a whole analogous story you can tell where you actually do that. I think, is that what you meant?
Probably.
Yeah.
I'm trying to figure out what would be the more general context here.
Right. And then when you look at these gauge actions, they will be preserved, but up to some cocycle conjugacy.
What do you mean by cocycle conjugacy?
I mean that. Sorry, I'm going back and forth, but I'm just looking at this. So, for example, here I have that the gauge action is exactly mapped to the gauge action, or exactly preserved. But when you look at these only up to Morita equivalence, then you might have to add in a cocycle in the sense of an action. And there might, so I'm not sure exactly, but there might be some cohomology information that needs to be taken care of.
Could you repeat what would happen then to these continuous orbit equivalences
So the
in this
So the
more
con-
flexible situation?
so the continuous
said
orbit
something.
equivalence is they should be seen as analogous things. So continuous orbit equivalence works when your shift operation is a local homeomorphism, so it's irreversible. But the flow equivalence, the other side of the story, is when you look at the bi-infinite sequences. I've only looked at right infinite sequences. So when you look at bi-infinite sequences, then your shift operation is a homeomorphism. And then conjugacy means something else. And the replacement for orbit equivalence is flow equivalence.
Thank you.
So they are somehow structurally related.
Okay, thank you. Let me ask once more if there is anyone online that has a question, because I personally cannot see the online feed. So if not, then let us thank the speaker again. Thank you so much. Okay, and this concludes the morning session. Thank you.
Bye.